This video is going to cover section 1.5 and section 1.6. 1.5 and 1.6 deal with order of magnitude, and significant figures. I figure that these are closely enough related that I want to talk about them together, because I don't really want to talk about order of magnitude without being able to use scientific notation, which I'm going to introduce with significant figures. I also don't think that you can really talk about significant figures without talking about precision. All right, so for example, I have here a simple ruler, right? So I'm going to take it, and I'm going to measure my pen in centimeters. So let's see. I'm going to line it up there. I'm going to read off that it says 16.6. That's what I'm going to go with. Oh, actually, I put it on the one line instead of the 0 line like you're supposed to do, so that you're not going from the end of the ruler. So it's actually 15.6. So my pen is 15.6 centimeters long. All right, so that's fairly believable. Now, what if I took this same ruler and I said, my pen is 15.61273 centimeters long? Do you think that I can determine that with this ruler? All right, so this is the idea of precision. How many places do I know the value to? Right, if I get in my car and I drive to Lexington and I tell you down to the centimeter what my odometer reads, that's similarly, it's nonsense, right? It's nonsense to say this with my ruler. But I could find a more precise instrument. For now, I'm just going to call them digits. In general, when making a measurement, you estimate one place value past the lowest mark. That's kind of the rule of thumb. If you have a digital instrument, then the paperwork that you have on it will tell you what its accuracy, what its precision is, and what its accuracy is. So I want to talk about also what's the difference between precision and accuracy. So we just talked about precision. That's how many digits you can determine a value to. Accuracy is how correct it is. So let's call this how much information. And this is the quality of that information. So a visual aid I like to do with this is imagine you have a dartboard with a bullseye. And we're aiming for the bullseye, right? So let's say we get a dart here, a dart here, and a dart here. It's a pretty large spread, but they are centered on the bullseye. So this I would call accurate, but not very precise. Now let's say over on our other dartboard, they all hit in the triple 20. But remember, we were aiming for the bullseye. So it's very precise, right? They're all right there in the same area, but it's not accurate. Because we were trying to get the bullseye. And this one's not very precise because it covers a big area, but they are centered on the bullseye. All right, I think that's enough about precision and accuracy. I want to talk about significant figures. So we just introduced this idea talking about precision, about the number of digits you have and what you can count on. So when we talk about significant figures, if I have 3.1700, let's pick out some more numbers. Let's say we have 0.0317, and we have 0.001. Let's try to determine how many figures are significant here. And this has to do with talking about your precision. So in this first one, when I write these zeros here, that's saying that I know those values to be zero. This is not 3.172. It's not 3.1751. It's 3.1700, possibly something, right? So our significant figures is 5. In this one, how much of this carries information about the measurement? These zeros in front don't carry information about the measurement. They carry information about the scale, right? So the only ones that matter here are these three that carry information about the measurement. And notice that that's different than up here, right? In this example, these tell me about how precise the measurement is. I know out to 1/10,000th the value. In this one, I know out to 1,000th the value, but this one is really just about place value. I only know the 3 sig figs. And then this last one, there's only one significant figure. So it's easy to identify the number of significant figures. The only tricky thing is that these zeros matter because they're telling you that you're more precise. So there are two calculations that you might have with significant figures that you need to be able to carry through. So addition and subtraction and multiplication and dividing. When you add, and we'll just stick with the numbers that we have. Let's say we take 3.1700 and we're going to add 0.0317. And we're going to add 0.001. All right, what's this going to be? 3.2027. All right, how many of those significant figures do we keep? Oh, did I say it incorrectly before? I think I said this one to the thousandths, but that's a 10,000th also. Sorry. It's the way that I had it lined up. It didn't make sense. So in the first one, we're saying that we know the value to the 10,000th. In the second, we know the value to the 10,000th. And in the third, we know to the 1,000th. So that means we can only keep to the 1,000th place. So we're going to round this to 3.203. We're going to keep that 1,000th place. So in words, that is keep the smallest place value that is in all terms. Right, so the smallest place value that's in all terms is the 1,000th place. Right, because this could be 0.0012, 0.0015. We don't know because we haven't measured it that precisely. So we can't make a claim about what that 10,000th place is. All right, so now let's multiply them. If we were to take 3.1700 times 0.0317 times 0.001, and put that one in the calculator and see what we get. We get 0.000100489. Right, that's just calculator spew, right? How many significant figures do we actually have here? All right, well, we talked about the number of significant figures before. And notice over here, even though this one has 5 significant figures, this has 3 significant figures, and this has 1 significant figure, our final answer had 4 significant figures because we were looking at the place value. When you multiply, you keep the lowest number of significant figures. So here we have 3 sig fig. Here we have, or sorry, that's 5. 3 sig fig and 1. So when we would round this, we would round it to 0.0001 would be our rounded value here. So when you multiply, you keep the smallest number of sig fig. All right. Anything to add on that? I think that covers all the questions about sig fig that might arise. So let's talk about order of magnitude. And I feel that this is closely related to sig figs because we're going to talk about scientific notation, right? In scientific notation, you're going to write, how do I want to say this? Let's say A times 10 to the B, where A is a number between, and I'm going to say strictly between, so I'm just going to write it out, such that it's greater than 0 and less than 10. Strictly greater than, strictly less than. So that means I can't write 0.1 as A. Actually, that works for that. It's strictly between 1 and 10, sorry. That's why you have to think about it, right? It's strictly between 1 and 10. And we'll do some examples so that makes sense. B here is the order of magnitude. Maybe if I toggle my pen, it will start working. All right, let me stop the share and share again so that it might work. Okay, seems to be working now. All right, B is the order of magnitude. So let's look at some of the numbers we were just using if we were to write them in scientific notation. We had 3.1700, we had 0.0317, and we had 0.001. Right, those were the numbers we were using, yes. So let's write each of these in scientific notation. Well, this one is already a number between 1 and 10. So we have 3.1700 times 10 to the 0. 10 to the 0 is 1, right? So this is your unitary order of magnitude, unit 1, right? If we were to look at this one, we're going to have to multiply it by 100 to get to a number between 1 and 10. So we would say 3.17, but we had to multiply up to it by 100 to get to that. So we're going to need to multiply by 10 to the minus 2, which is 1 over 100. And notice here in scientific notation, this is the number of significant figures. And for the last one, we'd have 1 times 10 to the minus 3. And again, 1 sig fig, right? So you wouldn't want to say 1.0 again, because 1.0 would claim that you have knowledge about that next place. So now that we've got scientific notation and significant figures under our belt, I want to work through an example. So the force of gravity on the surface of the Earth is given by this equation. Not the force of gravity, sorry. The gravitational field strength. I'd have to multiply by the mass to get the force. We'll do that later. I just want to do it as an example because it's like nice for numbers. So big G is 6.67 times 10 to the minus 11 newtons meters squared per kilogram squared. The mass of the Earth is 5.97 times 10 to the 24th kilograms. And the mean radius of the Earth is, oops, I forgot my square. The mean radius of the Earth is 6.37 times 10 to the 6th meters. And then that's going to be squared. So the other thing that it talks about in section 1.5 is estimation. So I look at this and I say, I can probably estimate this pretty well. Like all of these are around 6, right? I'm dividing by 2 factors a little bigger than 6. I'm multiplying 1 factor slightly smaller than 6, basically 6, and 1 a little bigger. So let's first break this up with scientific notation. If we break this up using our scientific notation, I can say 6.67 times 5.97 over 6.37 squared times 10 to the minus 11 times 10 to the 24th over 10 to the 6th squared. And then I could bring my units over too. 1 of the kilograms cancels, both of the meters cancel, and we get newtons per kilogram. Right. That's why I said if we wanted the force, I'd have to multiply by the mass. This is what's nice about scientific notation. I can now look at this and figure out the order of magnitude of the force. Or sorry, I said force again. the field strength. So 10 to the 6th squared is 10 to the 12th. 24 minus 11 is 13, so this is 10 to the 1. And now we can look at the stuff I was talking about, how these are all close to 6. And I'm dividing by this one squared. If we actually plug these in, what do we end up with? I'm going to say these are all close to 6, and I'm going to make a guess that it's basically 10. So if we take 6.67 times 5.97 divided by 6.37 squared, the actual number we get here is 9.813 and more digits. I've done it to 3 significant figures because of the values I use. So let's stick with 9.81 newtons per kilogram. And that's the gravitational field strength on the surface of the Earth. All right, but the point I'm trying to make about estimation is when I look at these and I say, okay, 6.7 times 6 divided by 6.4 times 6.4 is close enough to 1, right? At least order of magnitude. And then the scientific notation allows me to easily identify the order of magnitude. Negative 11 plus 24 minus 12 gives me 1. So right away with order of magnitude, I'm saying it's about 10, and you get 9.81. It depends on how precise you need to be. All right, I think that covers everything for chapter 1.